So today we have Xiao-Gang Wen, who earned his bachelor's degree in the University of Science and Technology of China, and then came to the United States via custody program and studied in Princeton University under Witten. And Xiao-Gang proposed the idea of topological-order, which is important, very important in the condensed matter theory. And today his topic is the symmetry topological-order correspondence. Let's welcome Xiao-Gang.
Yeah, thank you. Yeah, it's a great pleasure to come to this Princeton summer school. Actually, a lot of lecture are really connected. So the thing I'm going to talk today actually already appeared in various previous lectures. Today I'm going to talk about this symmetry topological-order correspondence, which kind of similar to this ADF CFT correspondence. And so in the first lecture, I will mainly discuss this topological part. In the second lecture, I probably will mainly talk about this correspondence part. And it turns out that this correspondence already appeared in one of this 2015 paper, which represented this figure. And at that time, somehow we know the answer, but we don't know the question. And so it takes 4 years to realize what is the real question, and we find this happened to be the answer for this correspondence. But let's first talk about some basic things. There's 3 kinds of quantum phase, means a phase at a 0 temperature. And we have a gap phase, and a gapless phase, and a gapless phase. And the gap phase, basically, we have a energy gap in the many-body spectrum. So below energy gap, there's not much. So there's no excitation except once the DNA. So in a sense, the gap phase are trivial. The gapless phase have 2 classes. One class is a gapless phase with a finite mode, like a superfluid Dirac fermion and the critical point. So those are kind of simple. But there's another gapless phase, which you can asymmetric study first, actually. Is a gapless phase with an infinite number of modes, like Fermi liquid. And this is much more complicated. So my talk will be the first lecture. We'll talk about the gap phase. In the second lecture, we'll try to using this symmetry topological correspondence as a way to handle gapless phase, but only this simple one. So the
last part is for the third lecture. The last part is for the third lecture.
No. Last part is completely open. So but it's the first thing you learn in solid state physics. So that's you learn complete open problem. And a standard, very interesting gap phase is really quantum Hall states. So let this chi n to be the wave function for the n field lambda level. Then the Laughlin state can be written as a chi 1 to the nth power. Okay, and so you can also have this explicit form. And this one explains the filling fraction 1 over n m quantum Hall states, because when you raise into the mth power, electron have mth order 0. They stay further apart, like Yang mentioned. And so the filling fraction density is lower, you get a lower filling fraction. And this wave function also gives us a simple explanation of a fractional charge, because if you remove one electron, then one of the coordinates z just became c, just a label. And from here you say, yeah, this wave function describes a hole at c. But then if it's into raised to nth power, you can split c into m part. Then you can get m holes, m different holes at different locations. And each one carry 1 over m charge. They also carry fractional statistics. It's no longer Fermion anymore. It's So this may be the simplest three-line explanation for fractional charge and the fractional statistics. Okay. And so actually, this gave us this so-called abelian anion. But even more exotic, non-abelian anion can be can appear, can be realized in a similar fashion. You know, Jane proposed that the product of this gapped integer quantum wave function is also gapped. So like this, we have integer quantum Hall states with an n-field lambda level, but they raised to mth power. We say this kind of wave function also represent a many-body wave function, but even a gapped state for certain Hamiltonian. So if you accept this assumption, then we find a certain kind of wave function construct this way, like this chi n raised to mth power. Actually describe non-abelian states. And if both m and n are not equal to 1, something bigger than 1. And the way we show this is that to using this Slay boson theory or parton theory, because chi n raised to mth power we can view as we split electron into m part. Each parton are described by n-field on the level. Then we have a n copy of this. Then we combine this parton into a single electron. That's a raised to mth power means that all these z's in different parts of chi n all identified. So this we cut the electron into m parton, then recombine. And why we want to do that? Because recombine electron into parton can be done using glue, this SUN gauge field. And so then you can using this detour to derive this SUN Chern-Simons theory. And this n actually happened to be this level of Chern-Simons theory, and that gave us non-abelian statistics. So this is one way to get a non-abelian statistics. Another way to get a non-abelian statistics is proposed by Moore and Reed, and which is really using the correlation function of component field theory. Usually, correlation function say two operator correlation function, 3 operator correlation function, and here is a why not n operator correlation function, which n is 10 to 22, and so then you get a huge n-body correlation function, but view this correlation function as a wave function, and then let's say that is a many-body wave function of certain quantum Hall states. Why not? And in this case, it turns out that in this correlation function, there is some kind of multi-valueness in the wave function, and this multi-valueness gives us a branch cut when you and if you conjecture that is a big conjecture. If you conjecture this multi-valueness somehow is related to non-abelian Barry space, then you have non-abelian statistics basically. Yeah, when you break into particle, you get a different sheet in the multi-valueness. That's still some kind of non-abelian statistics. And so it turns out that this Faffian wave function and this wave function, the this chi2 squared times chi1, they both have filling fraction 1/2. They have so-called non-abelian Ising anion. And this chi2 to the cube, this wave function, it turns out to have this Fibonacci anion. So another anion is more exotic. Yeah.
What is D here?
Yeah, D is so-called quantum dimension. So people usually describe a non-abelian anion as you have a non-abelian Barry space. Some unitary matrix is not one-dimensional when you're braiding the two. But actually, I think it's much better to view non-abelian anion as the anion carry internal degree freedom. But you may say, well, electron carries spin 1/2. That's also internal degree freedom. Why we call electron fermion, not anion, non-abelian anion? But indeed, the mathematicians call electron non-abelian anions because of this internal degree freedom. And but however, for these two anions, it's more strange. The internal degree field is not even integer. Electron is 2. But here is a square root 2, and this is even more strange. It's this kind of golden ratio, something. So that's why it's called Fibonacci anion. So this is not some Fibonacci sequence up here. Okay. So therefore this we need to confirm is this do we really have a non-abelian anion? Because there's some assumption went through it. It turns out that again this is it turns out that there's a correspondence between the quantum Hall state and there's some edge states, which is some kind of conformal field theory. And so it turns out that so-called abelian quantum Hall states always have an integer number of modes, because the edge states can be viewed in a hydrodynamical sense. The quantum Hall droplet can change shape. So you have a surface wave on the droplet, that's give you this phonon mode. But when you have a abelian quantum Hall state, the number of phonon mode always integer. But however, so if you find the edge mode have a fraction number of a phonon mode, then that implies a non-abelian. So this can be checked numerically. So we can just put the quantum Hall state on the computer. So 8 electron on 20 orbits, and then we get this. This is the spectrum. So that's a 0 energy. So we have this ideal 3-body interaction. So the ground state always has 0 energy. So this is energy gap. Then the ground state have some small angular momentum. So that's a compact droplet, circular droplet. When the droplet changes shape, the angular momentum increase, getting bigger droplet. So the state at a different angular momentum is have degeneracy. Those are degeneracy. That's basically the spectrum for edge excitation. And how do you know how many phonon branch? If the degeneracy is a 1, 1, 2, 3, 5, a partition number. If you see partition number sequence, that is one mode of phonon. And this one is more than partition. So there's more than one mode of phonon. But less than 2 mode of phonon. Now 2 mode of phonon, you can tensor product 2 partition number together, you get a 2 mode phonon. But this one is less than 2 mode of phonon. It turns out that it have a 1.5 mode of phonon. So it's kind of a funny thing. So there's a kind of fractionalization of edge states, and also can be viewed as a one chiral phonon or 1 chiral Marana fermion. Marana fermion is like half phonon mode. So this kind of numerical calculation kind of confirm, yes, we indeed have this non-abelian statistic, but indirectly, you know, to show to observe non-abelian statistics directly by experiments is pretty tough. You know, at the moment we don't have a very good practical way to see that. But you know, Kun Yang mentioned this, maybe there's another gravitational mode. Again, that's an indirect way. So so those are some examples. But when such kind of exotic thing like fractional statistics, non-abelian statistics, fractional number of edge mode, those kind of things appears, you may say there may be something more fundamental. So maybe this the quantum Hall state is really a new kind of state beyond the symmetry breaking order. So those phenomena are very different from what we see in symmetry breaking order. So that motivates us to introduce this notion of a topological order to describe this kind of many-body states. But actually, what was really happening is that those are experimental observation of a quantum Hall effect. You have a very precisely quantized plateau, which it represents some kind of a new phase of matter. What happens is that this plateau became more accurate when the sample getting dirtier. Means you don't have you have less symmetry. Actually, you don't have any symmetry except this conservation of electron number. And so looks like this different plateau is not associated with symmetry breaking. So that itself suggests that the different plateaus should represent a different order beyond the symmetry breaking. So that's really the motivation for this notion of topological order. But what is a topological order? And I think we have a similar problem in superconductor. What is a superconductor? It's a superconducting. That's superconductor. But what is a microscopic reason for superconductor? And that's mechanism. And it took, I don't know, 40 years to find the mechanism, which is a electron pairing. And so then there's a similar issue. We have this new phase matter called topological order. What is a microscopic mechanism? It turns out that the mechanism is this long range entanglement. So somehow this topological order really represents this pattern of long range entanglement. So different pattern of long range entanglement give rise to different many body phase matter. So at that time, 89, I don't know the entanglement, and so entanglement is not very fashionable, and so in hindsight, maybe we really should call topological order the entanglement order. It's really order in the many body entanglement.
Xiao-Gang, I think the date is wrong.
Huh?
1911 for superconductors. No, 1904.
I think this paper is 1911.
1911.
Okay.
Yes.
Okay. But somehow I don't know where, because on this paper somehow there's a 1904. Okay. Anyway, yeah, so really should be 1911.
I think we don't.
Yeah.
Maybe we should check.
Maybe I should. Actually, this paper is not. I don't know. It's maybe not even not in the regular journal. It's some kind of report of some university research folder or something, archive. Anyway, so so actually here just want to mention that although the topological order really motivated from from high-T superconductor, from chiral spin states, and also from quantum Hall states, but actually the first experimental example of topological order is really the superconductor. The superconductor realizes so-called Z2 topological order, and so it's really the first example that's beyond the symmetry breaking. But the irony is that the symmetry breaking theory is developed, motivated by this superconductor, and by ignoring the dynamical electromagnetic field. So certainly, if you include dynamic electromagnetic field, the superconductor is a Z2 topological order. It have a bulk for quasi-particle, which is a Z2 charge, and the pi flux is a Z2 flux. So that's really a topological order. But however, in the textbook superconductor, people always ignore the dynamical gate field. So in the textbook superconductor, it's a symmetry breaking state. So I have to distinguish the textbook superconductor and the real life superconductor. And in particular, I want to say that although this Ising type of topological order, just mentioned, I actually have probably, I think now people have a consensus, really have a realization, which is first discovered in this Bob Willis experiment in 2009 at some filling fraction 1/2 states. But it takes a long time. No, maybe from 2017, we start to see this half integer, half branch edge states. And that's kind of some kind of a confirmation. Maybe this one is really a non-abelian states. And nowadays, there's a lot of experimental efforts in the spin liquid, also in the quantum simulator, try to discover more topological states. So what is a theory for topological order? Because when you say many-body entanglement, it's just a words. What is the concrete data to label different many-body entanglement? So that is a question. And actually, there's two approach. One approach is based on this degenerate ground state. It turns out that when you put a quantum Hall state on the Riemann surface with different genus, you make a different degenerate ground states. And from the different degenerate ground state, you may develop a theory. And so that's a one kind of theory. We will call this moduli bundle theory. It's kind of scary name. Then another theory based on excitation. You know, the quantum house, they have many excitations. If you consider all their excitations, then those all their excitations together actually are described by something. You know, yeah, this already sounds a bit scary because usually a state have infinite number of excitation. When you put all of them together, and you have a lot of data, and certainly that will describe ground states, but that seems very difficult. And but this direction turned out to be a good direction, and the theory describing all the excitation is called the modular tensor category theory. And so then we can use the modular tensor category theory to describe topological order. So that's basically two way to describe a so-called many-body entanglement. So what is the theory for many-body entanglement? So this is a kind of a theory. I just want to mention that the modular tensor category theory actually developed in a kind of strange way because in this paper, people studied the so-called rational conformal field theory in a very systematic way. Then they find that there's a structure for modular tensor category in it. And then in the Williams paper, show that there's a Chern-Simons theory or topological field theory and the conformal field theory have a very, very close relation. But the Chern-Simons theory is known to describe ambience. So it turns out that this modular tensor category theory can also be viewed as a theory for ambience, not just a theory for conformal field theory. Actually, it's more of a theory for ambience, but the first discovered in conformal field theory. It's kind of interesting thing. Okay, so what is a Grancy DNSA? Grancy just Grancy DNSA. What's about it? The thing is that if you want to use Grancy DNSA to describe quantum Hall states, there is some psychological barrier because Grancy DNSA is viewed as a finite size effect at that time because this. It's known that the ground inertia of quantum Hall state on the sphere and on the torus are different, and there's a big argument about it. So what is it? How to understand this? And also it's also known that the ground inertia and the torus coming from center mass motion. Quantum Hall state have a lot of degree freedom. It's a many body electron, but their center mass there's 1 degree freedom. They move in a certain way in magnetic field. So there's something. But it looks like this center mass motion or this quantity energy is not a thermodynamical property. It's not a property of a phase of matter. It's some kind of a marginal descendant property, some finite size effect, something else. Okay, I think what convinced us, yeah, this quantity energy indeed is something described a phase really because the quantity energy is robust against any impurities. So it's a degeneracy not coming from symmetry. Actually, we don't need any symmetry. It already have that. So there's a many argument. The one argument actually is based on this Landau level picture, but in this maybe it's a Landau gauge. I don't know. Certainly we have this many-body wave function which was this gauge. In this gauge, we have translation symmetry in x direction. Then the Landau level states can be labeled by the momentum kx. Kx still conserved, at least for this wave function of this Hamiltonian. So those lines, those stripes are just a single body states with different value for kx. Then at say 1/3 filling fraction, 1/3 those lines are occupied. May not be like equal spacing, but there's fluctuation. But roughly they occupy. Okay. Then we find that we can thread pi flux. You already seen this several times. When you thread the pi flux, then that's like a pump of kx. When you're threading a flux, kx is increased. When you thread a 2 pi flux, then the ks go from 1 single body level to next single body level, just shifting up by 1. And so after threading this 2 pi flux, you get another many-body states. So this many-body state is a degenerate ground state. That's one of the degenerate ground states. They are orthogonal because they have different kx. You can compute what is the difference in Kx. And a certain difference in Kx is because each level is shifted by 1. So it's a 2 pi over Lx, that's the quantization of Kx, has a number of electrons. Okay. Then you plug in the numbers. It turns out that this number happens to be this Ly over the magnetic line square times 1 over m. So the delta Kx is different. But what is important is the difference is macroscopic. It's a linear in size in y direction. And therefore, for a large system, the impurity scattering cannot connect these two ground state with such a difference of Kx. Okay. And so therefore, even with impurity, we have to do this the high order perturbation of an order Ly to split degeneracy. So that's why we get this degeneracy is kind of exponentially small. Yeah. And so this is a very simple argument, but on the other hand, I think this argument really reflects some pretty interesting feature. One is a UVR mixing, and another is a non-commutative geometry. So somehow this topological degeneracy actually from deeper level really coming from this UV non-commutative geometry of first order level because x, y coordinate do not commute. And that also led to UVR mixing. So maybe this is the more fundamental reason for this. And so what I really try to say is that there is a non-commutative quantum field theory behind this argument. And it's kind of interesting to formulate such a non-commutative quantum field theory can develop some better understanding of this argument. Yeah. So here we just emphasize this degenerate ground state, but here I just emphasize that actually the degenerate ground states led to this moduli bundle theory. So this moduli means a moduli space. The moduli space again scary name, but it just means a space of Hamiltonian. That's it. So, but however, this Hamiltonian just not absolutely Hamiltonian. It's a gapped Hamiltonian. So not just all the Hamiltonian, just a gapped Hamiltonian. And the modular space parameterized by the coupling constant in the gap Hamiltonian. And so from that point of view, we see that for every point in the moduli space, we have this degenerate ground state, which is a vector space. When you're moving the parameter, you get another vector space attached at another point in the moduli space. So what we get is a Fourier bundle, vector bundle over moduli space. This vector bundle may be curved, may have a lot of properties. And actually, the proposal is that this vector bundle encode this many-body entanglement. Maybe all the information about the many-body entanglement. So by studying this vector bundle over moduli space, we can develop a theory of a topological order. So this is what we call this moduli bundle theory. So let's just go through this a little bit more. That is so in this case we choose our parameter to be inverse mass matrix. So this Gx, Gyy just a mass matrix, just a mass. And then we can put this mass matrix into this 2x2 matrix, which depends on tau. So using this tau x is a real part of the tau, and tau y is an imaginary part of tau. It's a complex number to parameterize this mass matrix. And so then we get the moduli space of described by this upper half plane. The upper half plane just describes some kind of some mass matrix. Okay. But however, it turns out that for different mass matrix at different value of tau are connected, they differ by the coordinate transformation. So they're really describing the same system. Okay. So therefore, actually, the modular space is not just upper half plane, but actually there's a shaded area, like a Boolean zone. We kind of quotient out this transformation because those are regarded as equivalent. And so then we have this moduli space. So we have a vector bundle on this kind of moduli space, and now may describe quantum states. So the vector bundle on this moduli space actually can be used as a way to describe topological order in 2 dimensions. So this is basically the idea. So what is this vector bundle? Vector bundle actually is described by the curvature. So what is curvature? The curvature is just a Barrett space. The Chen number is also a curvature. Okay. But however, there's 2 kinds of Barrett space. We can change our mass parameter going through a small loop inside this moduli space. When you're going through this small loop, the degenerate ground state would twist around and come back. And when they come back, they differ by the unitary matrix, n by n unitary matrix, where n is the degeneracy. But this n by n matrix cannot be just a pure U1 phase in this case. Why you say this is a pure U1 phase? It's really because of following. Suppose you get a non-trivial phase, some non-trivial, not just U1 phase, something non-trivial. Then you can imagine you do this atomic physics experiments. You do this Fourier system. You just go around this loop over again as a periodic system. Okay. And then when you go over this loop over again, then you find this. You can view this non-abelian phase of going through this small loop as time evolution for some adiabatic evolution of Hamiltonian. And so you can imagine you have effective Hamiltonian, which is time independent, but approximate this Fourier system. But this effective Hamiltonian have a non-trivial time evolution matrix. That means this ground degeneracy are split. This split. But however, this motion around the small loop is like perturbation. It induces some kind of shortening interaction effectively. So that's then you'll say, oh, this ground degeneracy can be split by shortening interactions, and which contradict with our previous proof that the degeneracy are robust. So therefore, when you have a topologically robust ground degeneracy, it's implied that this non-abelian Barrett phase going around a contractile loop is always a pure Young phase. The energy level can shift globally together up and down, but they cannot split. So that's to get a non-trivial non-abelian Barrett phase, we have to go through non-contractile loop. One way to go to non-contractile loop is following. Let's assume we deform our system. This is a torus. We deform that into another system, also on a torus. However, if the top torus, the lower torus can be glued after some non-trivial coordinate transformation. So I'm using non-trivial coordinate transformation to glue 2 torus together. And this non-trivial coordinate transformation is a non-trivial map from torus to torus. Mathematics is called the mapping class group. And so these 2 are 2 non-trivial mapping generator of a mapping class group. One is 90 degree rotation, another shear deformation of the torus. Okay. If you do that, then you will get this non-contractile loop. Okay. So therefore, this non-contractile loop coming from this mapping class group elements. And for each mapping class element, we get a non-abelian Barrett phase. And it turns out that the torus, this mapping class group, is SL2Z. So therefore, this non-abelian Barrett phase gave rise to representation of SL2Z. This is something much more concrete. We say, oh, there's a 2-dimensional topological order. Something many-body entanglement is something really, we don't know what is this. But now at the end, it's a representation of SL2Z. Something very concrete. So different SL2Z representation just give us different many-body entanglement. That's something, yeah, we can lay our hand on. Yeah. But certainly, this argument also says that to be more precise, we should really say projective representation of SL2Z. Because its U1 phase is arbitrary, it's ambiguous. So strictly speaking, it's a project representation. But on the other hand, SL2Z do not have a project representation. Okay. So I don't know how to say that proper. Actually, SL2 they have a project representation, but however, all the project representation can be deformed to the representation. There's no non-trivial class of a project representation just by themselves. Yeah. So it's different from other group. But anyway, so there's some story like that. Maybe here I just want to also mention that I think this U1 factor we kind of ignore is actually important. This U1 factor is a curvature of is a trend number. They were a trend number. So integration for U1 factor integrate over this Boolean zone, not Boolean zone. This moduli space is a trend number. Turns out this trend number should be the central charge, or should give us how many phonon branch at the boundary. So this is to me, this is kind of amazing. It's well known, but on the other hand, I think it's very fundamental. From many body physics point of view, this kind of U1 curvature relate to the edge spectrum is almost incomprehensible. You know how that connection is there, but it's there. You know, and yeah, so it becomes really strange. Yes.
Does the mapping class group describe both bosonic and fermionic systems?
Yes, but for fermion, it's trickier. For fermion, you need to change boundary conditions. So there's a mapping class group usually map one boundary into another boundary condition. But if you consider all four boundary conditions together, you get something. So but the fermion is a much trickier, yeah. And so this really is for the boson. To be simple thing, what I'm describing here really mainly for boson. Yeah.
And the four boundary conditions like periodic.
Yeah. For fermion, you get a proper theory when you consider all the boundary conditions. Okay. If you don't consider all the boundary conditions, you get something kind of half. You get half theory. Yeah. And okay. Yeah, so this is what I say. Yeah, we just conjecture that the topology-order completely characterize this mapping class group. But with one catch, not just for torus, we have to do hygiene Riemann surface. For a while, people are hoping or dreaming torus is enough, but actually later there's counterexample. Torus is not enough. Yeah, the mapping class group hygiene Riemann surface. And again, this is something very deep. That means we should consider all Riemann surface for all genus together as one object, not as many separate objects. The mapping class representation on all Riemann surface should be combined to the one thing. Actually, there's a mathematical direction. Try to view two-dimensional topology in this way. All topology are the same object, consider them together. And this kind of thing should be a proper theory for 2D topology order. But again, now you see it's pretty open. You connect to some pretty deep maths. Yes.
Can you explain how this relates to many-body entanglement again?
Okay. No. But I can give you one thing is that when you have unentangled states, you just have product states. Now you can imagine you do the operation I did. You can imagine a little bit, you should get something trivial. Yeah, because when you have unentangled states, those operations don't do anything. Yeah, and so this is like you don't have degenerate ground states. And when you do this vector bundle, there should be no curvature. You know, that's it's because what we do here is like changing boundary condition. And the products, they don't see boundary conditions. It just don't respond, very roughly. And so there's a many-body entanglement. It's not like a off-diagonal long-range order, but it's still something long-range. And so now you can see that how to detect, probe something hidden long-range. And so this kind of ground degeneracy by changing topological space and doing this mapping class group, it's kind of a topological way to probe this long-range feature. And so this is actually the main motivation why we're doing this. Yeah.
Xiao-Gang. So what kind of entanglement measurements do you have to do to characterize the topological order this way?
Yeah, maybe I should say there should be a third approach, really using entanglement point of view. Actually, recent year there's some developed by ASAC team and Xiao-Gang Wen and also McGreevy. They try to cut this many-body state in all different way, and then try to measure different entanglement. Yeah, I think Xinxi here also doing similar thing. Yeah, that's and so this then there's some development that if you design those cuts, probably you can recover, I think, all the data. People believe, yeah, all these ST matrix, this SL2 representation.
I mean, from Chern-Simons theory, and things that can be related to Chern-Simons.
Yeah.
You can do that by making cuts on.
Yeah, it's related to that.
Exactly. You can do
yeah.
This. You are proposing something more general.
Yeah, this I will come to the Chern-Simons. This a cut and surgery, and but the entanglement point of view have a different emphasis. They emphasize on the lattice. So they presume this quantum Hall state, many bodies can be put on lattice. When you do the cut, they really cut between lattice point.
You don't really need that. You don't really need that.
You don't really, but to make things precise, what they do actually is cutting through lattice.
Well,
I think they have the very fundamental assumption that the many body Hilbert space have a tensor product decomposition. So this is pretty fundamental. And from there, they can derive this entanglement theory. Then using entanglement to recover this. But however, this the Chern-Simons theory is a cut and glue. Yeah, I'll come to that. But which is very important. But that one, I think eventually, yeah, I'm not sure whether in field theory we will do entanglement. Do you assume lattice, or you secretly assume lattice, or you do something beyond the lattice? It's not very clear to me. You know, people do entanglement in field theory as well, but how, to which degree that is related to the assumption of a lattice UV cutoff is not very clear to me. Yeah. So yeah, so that's basically the next topic. You know how, you know, this ST matrix gave rise to, let me see. Oh yeah, this is here. Yeah, you know, for each topological order, you know, we usually have a representation SL2Z. You know, that ST matrix describing that. But however, if you just give me a SL2Z representation, ST matrix, they may not correspond to topological order. So there's a lot of illegal one. Only a small subset of SL2 representation correspond to topological order, and a lot of them do not correspond to topological order. So therefore, we need to find the condition, find some condition on this matching collapse representation, so that the SL2Z matrix, SL2Z representation, such that condition really describes topological order. So we are really looking for the condition to really have a complete theory. And so the one idea is that so we can have this torus, and the torus can be viewed as a sphere with a handle. We can make handle very, very thin. Then that becomes a sphere with two puncture. So there's a relation between the sphere with two puncture and the torus. Actually, again, this idea is very important. Remember, I mentioned that we should have a theory which regard all the 2D surface with different topology together. This is the idea. We can squeeze the handle into a line and remove them, then changing topology. That's how we go between topology. And here is a way to go from torus to the sphere with two puncture. But the sphere with two puncture is like with two quasi particles. So therefore, actually, for sphere with a two puncture, we also have a degeneracy. There's a ground degeneracy for sphere with two punctures. And we also have this vector bundle theory for this over moduli space. But now the moduli space is a sphere with a two puncture, three puncture, n puncture. They have own moduli space. And this kind of vector bundle theory is modular tensor category theory. Yeah, I try to explain a little bit. So as I mentioned, that the modular tensor categories are developed in the conformal field theory, and later we realized it's a connect to transharmonic theory and onions. So nowadays, this modular tensor category theory is viewed as a standard theory for two-dimensional onions. Okay, and in higher dimension, we have a particle-like onion and string-like onions and etc. And then we have this so-called higher category theory, some kind of generalization of that. Okay. And in the early days, actually, we already see this connection between these two pictures. Because when you have a torus, we can create a pair of onions, and then move one onion all the way around torus in x direction, or move one onion all the way in the y direction. We get this tunneling graph. So this onion path can be viewed as an operator. This U operator. And actually, this U, X, U, Y is tunneling X, Y direction. They do not commute. And the phase factor actually is a mutual statistics. It's like we can deform this path into this path. Then it's a linked loop. You're like moving one onion and another onion. That's a mutual statistics. And then we get this Heisenberg algebra, which do not have 1D repetition. And the repetition of this is given by this phase factor. That's given rise to degenerate ground states. So you can see this particle picture and the ground state picture are really have very intimate relation. Okay, so what is a topological excitation? Because now we want to use topological excitation to describe a many-body entanglement. And this is very much like using a defect to describe crystal. Okay, you should imagine, suppose we don't have an X-ray diffraction. And how do we study crystal without X-ray? We don't have any probe beyond, say, 1 micron. Then how do you probe crystal? Then you can imagine someone pretty smart say, oh, we can study dynamics of defect. Measure the heat transport of phonon plus try to isolate the contribution from the defect. Then from there we can identify whether it's a cubic or triangular. That's something we do here. Yeah. So this we understand the defect of this many-body entanglement pattern. Those are excitations. But what is a defect? What is an excitation? And one way to understand that those excitations is to using this so-called trap potential. The puncture is a mathematical way to say, yeah, we have a potential trap there. We can put some potential trap on the sphere, then diagonalize Hamiltonian with a potential trap. Then we may still get energy gap, with a trap. Then we say, in this case, the ground state will be the state with the excitation for the new Hamiltonian. So therefore, the new ground state subspace are really subspace for the excitation. Those are states with the excitations. So very simple things. But however, what I try to do here is that using this very simple setup, we can obtain a theory for modular tensor category theory. So modular tensor category is really just about the trap under their ground state subspace. That's it. That's the modular tensor category theory. So actually, it's really a theory for the excitations. So let's just go through step by step. Okay, certainly, when you have a trap, when you have a gap, we say this trap a quasi-particle. So first is really how to label things, how to label different quasi-particle. We just need to find a label, just like in many-body entanglement. The first question is how to give them a name so that you can write down something on the paper. Otherwise, you have nothing to write on the paper. And so here's the same thing. When you say, oh, we have a topological excitation of quasi-particle, so what do you write? And you can write A, B, cat, dog, something more sensible to write. So that's really what we're trying to do here. And so something we can do is we can use in trap Hamiltonian. We can write trap Hamiltonian, delta H. That's my quasi-particle. So then that's too detailed. We have a sense that different trap may trap same type of quasi-particle. So what do you mean by same type? Okay, same type means if you can deform a trap Hamiltonian without closing the gap, then we say this trap would trap same type of quasi-particle. Yeah. So therefore, we have a notion of a type. Yeah, and then this is very, very important. And we have infinite many trap Hamiltonian, but we only have finite types. Most traps are connected, can be connected without closing gap. They belong same type. Sometimes we get phase transition. Some two traps are so different. Deforming into each other, the gap close, get phase transition. Then we say, oh, these two traps trap a different quasi-particle. You can see that the type of quasi-particle and the phase transition are really related in that sense. Okay, and this is particularly important when you have a line string-like quasi-particle. There, the trap will be like a string trap. Then we deform trap Hamiltonian. Then there, when you have a phase transition on this one-dimensional line, then you get different particle. So you can see that the different string-like excitation basically like a different phase on this one-dimensional line. Yeah. So that's another way to one way to look at it. String excitation. Okay. But however, in particular for string excitation, there's two types of excitation. One we call the elementary, another we call the descendant. So so the descendant excitation can be viewed as something like a string excitation. We have some particle excitation. The particle may condense on the string. For example, the particle have an energy gap away from the string, but the particle get a negative energy on the string, energy getting lower. So strings have a lot of particle. That's a gas of particle. They interact, they form some kind of many-body state in one-dimensional string. And that is a descendant excitation. But however, there's another kind of excitation which is more topological than this descendant one. And this analog is that really in the 3D superconductor, there's a pi flux string. Cannot be viewed as some kind of particle forming some kind of many-body state along the string. So something different. It's more fundamental than that. But what do you mean by more fundamental? What is elementary? Okay, this really became a question. And when you're thinking about that, this means that it is something cannot end. Whenever a string excitation which are formed by particles, the descendant, that also means the string can end, can have an end. It's endable. Or means that the string can just disappear. But however, pi flux in the superconductor, they cannot end. It's always a loop, they cannot end. So this elementary excitation is an excitation. So sometimes you have a trap, which trap something which cannot end. And that is a more elementary excitation. Okay. So actually, in higher dimension topological order, we have these two types of excitation. And nowadays, people start to appreciate this difference and start to have a paper about this kind of excitation. And in particular, yeah, in this recent paper, this paper showed that the descendant excitation can be created by those so-called sequential quantum circuit. Yeah, and because this sequential quantum circuit can map a many-body phase to another many-body phase, and so we can do this. But however, but using sequential quantum circuit along the string, you cannot create this an elementary excitation. To create elementary excitation, you have to have a quantum circuit on the membrane. Then at the boundary of a membrane, you create this elementary excitation. So it have this kind of type. Yes.
Oh, so is what the circuit is doing when it goes along the string is it condensing the other anions along the string? Is that what it's doing?
I think this Yeah, I know exactly. I don't know, but more like I try to view this one is like a duality map. There's a one dimension. There's a like what this is a Kramer-Wiener transformation duality map, and they find this the duality map cannot be generated by this local unitary matrix circuit, but they can generate by this sequential quantum circuit. And then the different phase connected by duality map can be connected by this. So more of that flavor.
Okay, I think it's for this.
Yeah, it's more like that flavor. Yes.
Oh, yeah, I just want to confirm this string citation. If in the space-time picture, is that just correspond to some 2D surface?
Yes, 2D surface.
Condensed on this surface.
Yes. Yeah. Yeah. I'm rather describing the space picture. Yeah, in space-time picture, really is the surface and the anion canonical surface, and so actually this you can do that. This called a topological defect, and there are non-invertible topological defect and the non-invertible symmetry. So all those things are related to this kind of picture. Yeah. Okay. So yeah, maybe let me skip this. And okay. So another thing is want to say that actually there's a simple type of topologization and a composite type. And I think this is a notion kind of missed in condensed matter physics. And because excitation is well known in condensed matter physics, we study excitation all the time. And but what is a simple type and what is a composite type? Okay. And remember that the excitation is given by the trap. So when we have a trap, we have an excitation. But sometimes the trap gives rise to simple excitation. Sometimes the trap gives rise to composite excitation. What that means? Well, it's very simple. If a trap have an accidental degeneracy, then we say this trap a composite excitation. If the trap don't have accidental degeneracy, we say they are simple excitation. That's it. And so it's really that because actually the trap two excitation, the I is a one excitation, but the J is another excitation with a high energy. So in this case, we usually say we put a gap here. We say this trap I excitation. Okay. And in physics, we automatically assume we only study this stable ground state. Only stable ground state excitation will automatically assume this. We ignore this accidental degeneracy because they are not important. Okay. But the mathematician is more careful. They say if you fine-tune the trap, make I and J same energy, then what do you say? You cannot say my trap I. We cannot say your trap J. You say, okay, we trap this some IJ bound states, but they are not IJ bound states. They are something. Okay, so they write this is I plus J.
Xiao-Gang, don't you need a notion of symmetry?
No, we don't have symmetry. So here we really fine-tune the trap. There's no symmetry.
Yes, but when you do that, when you have accidental degeneracy, there is an emergent symmetry.
Yeah, and the ground states have symmetry, but excited may not have a symmetry. We only fine-tune things to make this ground state. Yeah. So there may be emergent symmetry. Yeah, you probably can say that. Yeah. So this is so therefore this accidental degeneracy is this plus, meaning plus. And so this is just something like some, I don't know what to say. It's like some mathematicians details which unnecessary detail, maybe can say. But actually, this detail actually is very important. It's a necessary detail.
So we have 15 minutes for conclusion.
Okay, yeah, sure. No, because 19. Anyway, so when you have a fusion, this notion became important. When you have a fusion, this notion became important. That is, fusion means you have a two trap. Okay. Then to two particle, when you two trap, each trap a particle, but when you stay far away, view the two trap as one trap, that's a fusion. But however, when a single trap can be viewed as two separate traps, that's like a kind of fine tuning. Yeah, it's a special case of one trap that have a two bump. Yeah. And so therefore, when we have a two trap viewed as a one trap, the two traps, they trap composite particle. So that means the fusion of two particles may not be just given as a third particle, actually may give this composite particle. So that's this sum. So I fuse with J bound state. Actually, the trap have an accidental degeneracy because the trap are separate, and have K1 plus K2, etc. Or we can use this Nijk. It's called the fusion coefficient, and this describe multiplicity of K, and then that's kind of fusion, define the fusion ring. So therefore, the fusion ring became non-trivial or interesting when we have a composite excitation. Yeah, and that is so that's led to fusion category basically, and so it's very simple. My point is it's a very simple. And actually, we do this. We are familiar with it because spin 1 half a fuse with spin 1 half. It's spin 0 and spin 1. You know, and this is one of a very standard fusion ring. Yeah, we cannot say 0 and 1 are bound state. It's just a sum. You know, many people write this as just a sum. You know, sometimes at the beginning I think of the superposition to wave function, and I get totally confused. Then after a few years, I start to realize this is not a sum; it's a direct sum. Yeah. So actually, this also represents something very important. That is, in this case, from this fusion ring, as the tensor product gave rise to direct sum, reveal internal degree freedom in a very secret way. You know, when you have a direct sum, that means, oh yeah, there's internal degree freedom. When you have a spin 1 half, use them as a one object, it's hard to say it have an internal degree freedom. The internal degree freedom is revealed when you fuse the two and you discover after fusion you get direct sum. So therefore, from the fusion ring, Nijk, we can recover what is the internal degree freedom. Yeah, maybe let me just go through this calculation. Okay, so so to do this, we can fuse many onions together. Okay, on the sphere. Okay, so when you fuse many onions together, and we can say, so in some sense, each onion secretly like a vector space. When you're fusing many onions together, it's like doing tensor product of vector space. Then we do the direct product direct sum decomposition of this tensor product. I try to recover what is dimension of a tensor product of the vector space. Actually, we're doing this calculation, but using fancier fusion category language, and that is so basically it's this. That is when you're fusing this I together, we get the direct sum of M. You know, M1. The direct sum actually labeled by M1. And how they appear is Ni to M1. Then this M1, each vector space can be fused with another I. Get another many direct sum, but now labeled by M2. You know. And then, so those are the direct sum decomposition of this fusion. And so therefore, the dimension of this vector space roughly is this each fusion channel just sum them together, just all different way fusion, just add them together. And but when I'm reading in this way, it turns out that this expression can be viewed as a matrix. Some matrix raised to n minus the power are taking certain component. Okay. And this matrix Ni actually is a particular way to view the Nijk. You know, we view Nijk as I labeled matrix. viewing another two index as a matrix index. And so there's one way to do that. But once you write this way, you find that this when n is very large, the matrix element of this nth power matrix is dominated by the largest eigenvalue. This bi is the largest eigenvalue of this n-line matrix. And so then we get some topics that the dimension of this fusion of those particles is symptotically is like a d to certain power. Yeah, d to certain power. So that is a quantum dimension I just mentioned before. Yeah, and if you do this Fibonacci fusion rule, Fibonacci fusion rule is like you have trivial extension when it gets fused itself, and trivial fused with non-trivial is non-trivial itself. But the non-trivial is non-trivial, you get a trivial extension plus itself. So have this kind of fusion rule. So then this matrix n phi is really have this kind of given by this. And you find the largest eigenvalue is this one, the next eigenvalue is this one, and that's how we get this quantum dimension, very strange quantum dimension. Okay, so certainly in higher dimension there's a braiding. So now I just sketch what I'm going to say. You have this braiding. So the fusion gave you as internal quantum dimension. I think that's a more important property of non-abelian onion. And the braiding is less important, it's harder to detect. But in two dimension, higher dimension, we also have a braiding. Okay. And then here, actually, using the fusion concept, we can describe a braiding, non-abelian braiding very easily. Because when you braid two onions, you may get a different phase. That's non-abelian statistics. But however, this phase depends on the fusion channel. If ij fused to k, if you know it's fused to k, this phase actually is abelian. It's some just phase factor. But ij may fuse to k, go to k prime. Then for when ij fused to k prime, you get another phase factor. So therefore, it's just so this non-abelian barrier phase. It's just a fusion-dependent U1 phase factor, so it's not very complicated. So that's one way to understand non-abelian, just a fusion-dependent U1 phase factor, almost like abelian onion. However, this U1-dependent phase factor also depend on this fractional spin. This non-abelian onion or abelian onion have a fractional spin. And they are related to fractional speed. Because of the following, when you try to move one particle around another, and this can be probed by rotating everything by 2 pi. Okay, so here is a picture. We have ij fused to k. I just rotate everything by 2 pi, the whole thing by 2 pi. We rotate the whole thing by 2 pi. Basically, this corresponds to the three things. We braid I around j by 2 pi. It's mutual statistics. And we rotate I by themselves, j by themselves by 2 pi. So that's these three operations like rotate everything by 2 pi. But we know ij fusing to k. So the whole thing, these three combination should give us rotation of k by 2 pi. So it's just give us these results. So you can see that if you know the spin of ijk, then we know the mutual statistics of this fusion-dependent mutual statistics, and that's basically characterized a non-abelian barrier space. Yeah. So therefore, fusion rule plus spin itself, that's almost characterized the non-abelian statistics. So this is like a simplified theory of modular tensor category. It's just a fusion rule we explained, and the spin for each particle. And that's it. So you may say, oh, what is modular tensor category? Seems really scary, but that's it. Well, it's not this. But it's a pretty good approximation of modular tensor category. So in some practical purpose, you can view modular tensor category theory. It's just these two data. And some people will hate me saying that. But anyway, so now I can really speak and see I have so many things. And But those are technical things. It's really describing this data of ST matrix I described from ground states. And Ni, Jk, and S for the excitation, they are related. So there's a lot of technical things. So I don't have time for that, but I'm glad I finished my setup. Okay, so by combining this, again, there's a lot of relation. And then so at the end, what we find is that maybe let's go through this. Yeah. So actually, these two set data really have one-to-one relation. And certainly, there's each data have a consistent condition. Like ST matrix should be from representation for SL2Z. And this Ni, Jk, and Si have many other consistent conditions. And then because these two set data are related, that is a formula. The S matrix and Ni, Jk are related, and this S matrix, this topological spin, the spin and the quantum dimension, they are also related. So there's a lot of magical relations. And when we combine two pictures together, then we find a lot of constraints on the ST matrix. And this allows us to really classify this modular tensor category. So this is a table of modular tensor category, but in terms of a quantum dimension and the spin. And recently, we find a classification modular tensor category up to rank 11. Means we have 11 anion types. Yeah, and so that's really combining these two pictures. And so 2007 we have a classification rank 4. 7 years later we get a rank 5. Another 80 years we get rank 6. And I think that now we have a rank 11. That's a. And rank 12 probably require another year or two. We'll see. Even bigger computer. But what I really try to say is that this now we start to have some comprehensive theory for the topological order or for the many-body entanglement. And so that's really correspond to. Actually, this table corresponds to the classification of all the two-dimensional gap phase for bosonic system without any symmetry. So we start to we can have a table for these many-body states. Okay, so in this afternoon, we'll talk about the next development. Means after 30 years of doing gap state, which is more or less trivial, so we can graduate to next level, gapless. Can we get a comprehensive theory for gapless states and how to approach that? Thank you.
I have a quick question. I thought there wasn't a classification of Xiao-Gang Wen has been working forever. Trying to classify essentially modular tensor categories.
Yes.
And since they seem to reduce or connect to the classification of two-dimensional CFTs.
Yes.
And there is no classification of that this is not a complete one.
No.
So in what sense do we have a classification? I think we know some classes of them.
I think this statement is pretty rigorous in not rigorous, pretty exact. Not rigorous. And but only for 2D.
Only for 2D.
Yeah, in 3D you have a fraction, which is non-liquid phase. So this assumes in 2-dimensional we don't have fraction phase, and then we can say that. But in 3D we have fraction phase. So then in 3D we can only say that we can calculate 3D gap liquid phase. Liquid means the ground state do not depend on the lattice too much. You can have random lattice which don't affect ground state property, and it's kind of like that. But however, for CFT is a different story. CFT, so there's an issue. Remember, multi-tensor calculus is invented to classify CFT.
Right.
And which that I really don't know. Yeah, this is a much more subtle question. But it turns out the multi-tensor calculus actually is a better theory for the TQFT. Yeah.
Than to CFT.
Rather than CFT. Yeah. But my next lecture is really try to say, can we using similar? Yeah, we already see the sign. Multi-tensor calculus maybe also can be used for CFT, and so we try to. So actually, the next lecture is about this question. Can you use multi-tensor calculus? Yeah. Yeah, but we try to push that direction. Can you use a multi-tensor calculus or higher tensor calculus to classify gapless states? That is yeah, it's more open. Yeah, it's more open.
Okay, we have another question online. So he's asking, is the quantum dimension usually less or more than the degree of freedom morphism?
Degree freedom of morphism. Yeah, I don't know. But I don't know what the degree freedom morphism means. I can only say quantum dimension always bigger than 1 for unitary theory, and it's sometimes integer and many times it's not integer. Yeah, and if it's not integer, it's more interesting because if it's a non-integer, that means the non-abelian barrier phase is complicated, and complicated enough you can do universal quantum computation. When the quantum dimension is integer, sometimes this non-abelian barrier phase is simple, so they do not give rise to universal quantum computation. Yeah.
Thank you.
Okay, so thank you, Professor.
Thank you.
So years ago, you probably know this work, that they wrote the paper with Xiao-Gang Wen and Rob Lee.
Yeah.
Where we used Chern-Simons theory to calculate, essentially, to try to extract, in terms of entanglement measurements, how the topological order is.
Okay, and the point central thing is the pointer?
No, this. Yes.
Okay, good.
And this is the macro. Do we turn this on? Okay, so I'll turn it on now.
Okay.
Okay. Yeah. Just put things. Oh yeah, that's also yes, that also works. I guess we are good.
Okay.
Yeah, we have the audience.
All right. Hello, everyone. 2 quick announcements about today. This is Sonia. She has done a great job organizing this entire event.
Thank you.
Two quick announcements. Our poster session is in the last kind of time slot, the talk time slot this afternoon. We would like posters to be hung up by 2:45, correct? You can hand your posters if you're presenting to Sonia before this. The other thing is we've had questions about when to check out of Baker Hall. You're staying in Baker Hall. The official time slot is 4 p.m. tomorrow. However, we've been told that they've been pretty lenient about this time slot, and there is a drop box in
71 University Place.
71 University Place. So if you need to stay a couple extra hours, whatever, feel free to do that as well.
That's it, you've got it.
That's it. Thank you.
Okay, so today it's our honor to invite Professor Philip Phillips, who received his bachelor's degree from Waitakere College and his PhD degree from University of Washington. And so he will give us 2 talks. The first talk is about the quadratic fixed point. for superconductivity and modulus. Thank you.
Thank you. Yes, I'm going to talk about something which I think is exact and rigorous. Since that seems to be in the air.
Except unlike things that I talk about, which are neither exact.
That's right. Where do I have this thing going? Not exact, rigorous.